Okay, so Unit 3 is going to focus around these ideas of work, energy, and power. Sometimes in the physics community, we just call this WEP for the kind of abbreviation of the, or kind of an acronym, right, of the first letters from each word, right? So we often will just call this WEP for work, energy, and power. Okay, so, and it's a progression. So we start talking about work, then we talk about its relationship to energy, and then power is actually related to both of these. Okay, and so we start way at the beginning. All right, so the first thing we're going to talk about here is work. All right, so the greater the force, the greater the effort you must exert. So when we think about work, if I were to ask you, you know, when I say the word work, what often do you think of, right? And everyone thinks about like physical exertion of something, right? Physical exertion of doing something, right? Lifting, pushing, right? Mowing a lawn, that type idea, okay? And the more that you put out there, the more work that you do. Well, guess what? Physics has a completely different definition. And in fact, some of the things that you would classify as doing work outside of physics, inside of physics is not work, okay? So this is going to be the basis for a definition of work, right? So the way we say it in the simplest case, right, it's the lowest case, work is done when a force is applied to an object and that object moves, okay, in the direction of the applied force. So before we talk about the symbol, the formula, and the unit, just a way to think about this, okay? So for work to be done, there has to be three things happening. First, you have to have a force. Next, you have to have a change in motion, okay? And the third thing is you have to have a cause. So the way this works out is that this force must cause this motion, all right? So if you find that the force that is applied to the object doesn't cause the change in motion, then that force does no work. Whereas if you find that, let's say you're pushing a couch, you are doing work because the force that you apply, so here you are, right, pushing the couch. Now here you are, right, pushing that couch. So this is your force. The motion is to the right, right? And so yes, this force is causing a change in that motion. We'll also talk about how does friction work into this, okay? But the symbol for work is just simply a capital W. The formula, you can get a little bit from that definition, okay, is just force times displacement. And the unit is joules, okay, which sometimes when we talk about work, we'll call it Newton times meter, but joules is the unit for all of energy and energy transfer, okay, because we're going to actually here in a second, we will redefine work in terms of energy, okay. So here's an example. It says an intern pushes a 72 kilogram patient on a 15 kilogram gurney, producing an acceleration of 0.60 meters per second squared. How much work does the intern do by pushing the patient and gurney through a distance of 2.5 meters? Now we're going to assume that the gurney moves without friction, okay? So we're letting the wheels move with no problem. All right, so easy way to do this, right? There's really two methods, and it all centers around force, okay? And so what happens is, remember, that the force exerted is simply m times a. So I can just either do one of two things. I can calculate the force here. Now we're looking at the patient gurney system, so we would have to add up the mass. Okay, so I do 72 plus 15 times 0.6. So it's going to be 87 times 0.6. So the force that the intern exerts is 52.2 newtons, and then I would plug that back in my equation. So they exert 52.2 newtons, and they do it a distance of 2.5 meters, and you would do 130 joules of work. Okay, so I said there are two ways. The second way to do it would just simply to take that formula for force and plug it in to the work equation. So you can see it just becomes MA delta X. But the MA, again, we're just going to do 72 plus 15 times 0.6 times 2.5. But notice we've done the same like math. And so this is still going to be 130 joules. Whichever method you take, right, this is 2 steps, and this is 1 step, right? So whatever method you use, you're going to end up with the same answer, okay? I almost prefer the 1-step method by plugging in the formula, because what happens if I make a mistake in calculating the force, or if I do it all in one shot, I know when I plug it into the calculator, I can limit it to a calculator mistake versus like an actual like mistake of miscalculating the force. Okay. So next example, early one October, you go to a pumpkin patch to select your pumpkin. Fitting that this past weekend was Halloween. So you lift the 3.2 kilogram pumpkin to a height of 0.80 meters to check it out. How much work do you do on the pumpkin when you lift it from the ground? Okay. So the way to think about it is if I'm lifting, right, what force do I have to apply to lift the pumpkin? Well, I have to apply the pumpkin's weight, right? At minimum, I would have to apply how much that pumpkin weighs. Okay, so I'm just going to put in the formula for weight, which is mg delta x. So we're going to do, say, 3.2 kilogram pumpkin. We'll use 10 for simplicity. And we're going to lift it 0.80 meters. And this is how much work are we going to do? We're going to do 26 joules of work. Okay, and you can see we had to do more force, right? We did 52 newtons worth of force here, lifting it or pushing it 2.5 meters. Okay, and here we did 3.2 newtons or 32 newtons worth, lifting at 0.80 meters, right? So if we kind of think about the relationships, right? And so what happens is if I leave the distance the same, if I increase the force, my work also goes up, right? And if I increase the distance that I push it, the force, the work also goes up. But on the other side, right, if I want to do the same amount of work and I increase the force, I just have to push it a shorter distance, right? So remember, when I do this kind of relationship building thing here, if you want to think about it, work is proportional to force, work is proportional to displacement, right? So as one goes up, the other goes up, but force is proportional to the inverse of delta 1 over delta x, right? And so that means if one goes up, the other will go down, okay? All right, so now one thing to note, right? Remember this idea of force cause motion, right? So if an object does not move, there is no work done, right? Remember, force, 3 things: force, cause, motion, right? If there's no motion, there's no work, okay? If there's no force, there's no work, all right? Now, we know that, the real world doesn't work in horizontals all the time, so not all forces are going to be exerted in one dimension. So when a force is exerted at an angle, only the component of the force that acts in the direction of the displacement is the one that's doing work, okay? And so if I just now say we're pulling a wagon, right? We're going to pull the wagon to the right. And so the only force of this applied force that will do work will be the Fx, okay? Will be the x component. The vertical component, and you'll see here in a second from the formula, will do no work, right? Because it's actually perpendicular to the motion, okay? So we can, change up the formula a little bit by adding in this angle aspect, So it'll be work equals F delta X. Now, typically, how do we add in an angle? We're going to do a trig function, right? So it's going to be F delta X cosine theta. And so the way to think about this, if the force is parallel, well, it's 0 degrees, and the cosine of 0, right, is equal to 1. If it's perpendicular, right, it's 90 degrees, and the cosine of 90 is 0, right? So if I go in the same direction as F and delta X in the same direction, I'm going to get an angle of 0. If they're perpendicular to each other, I'm going to get an angle of 90 degrees. All right, so let's see how this works in the equation. Okay, so it says in a gravity escape system, an enclosed lifeboat on a large ship is deployed by letting it slide down a ramp and then continuing in free fall to the water below. Suppose the 4,900 kilogram lifeboat slides a distance of 5 meters on a ramp that makes an angle 60 degrees with the vertical. How much work does gravity do on the boat? All right, so we're going to start with our formula. Work equals F delta X cosine theta. I know sometimes when we say it's measured from the vertical, we want to flip-flop the sine and cosine, but actually if you look at the way this triangle is created, here is let me do it a different color, right? One that will stand out a little bit more. Here's a good one for yellow. I don't like to use the yellow, but we'll use yellow here. So here is right? So if I draw in my triangle, this is the X component of the weight, right? And so that will stay in line where we can use cosine and not sine. And so all we're going to do, again, so the force will be the weight of the boat. Again, you can calculate it, then plug it in, or you can just plug it in, right, the formula here. So we're going to say mg delta x cosine theta. So it's 4,900 times 10. And it's going to travel a distance of 5 meters, right? So this is 5 meters. Cosine, and they tell us this is at an angle of 60 degrees. Okay? And so when you calculate this all out, you're going to get that gravity will do 120,000 joules of work on the boat, okay, and dropping it down into the water. All right, and so here's just a little bit more to do with the angle, okay? And so this says work depends on the cosine of the angle between the force and the displacement. Right, so and work can be positive, negative, or 0. Okay, so you can do positive work, which actually would add energy to a system. You can do no work, which doesn't change the energy, or you can do negative work, which actually takes away. And so positive work is done when the angle is from 0 to 90, but not including 90 degrees, right? So the way it works out, these are acute angles, right? 0 work is when the angle is equal to 90 degrees, right? And this is the perpendicular, right? And remember, cosine of 90 is 0. And then if you want to do negative work, you'll go above 90 to 180 degrees. And so these are obtuse angles. Right, and so the cosine of 180 is -1. Okay, the one force that will do essentially full negative, right, because it does go opposite the motion, is friction. Okay, and so now here's a simple ranking task, and then we'll break this video because I don't want this to get a little too long. All right. So this says each of the boxes shown below moves through the same horizontal distance d, and the force applied to each of the boxes is the same magnitude F. Rank these cases in order of increasing work done by the force F from most negative to most positive. Okay, so the way we want to look at it is how does the angle affect, right, the force, or how the angles affect. So this is a perpendicular angle. This is 180 degrees, right? This is an acute angle, so we're between 0 and 90, and this is 0 degrees, right? And so we can kind of look at how this does, right? So here, the work done, because it's perpendicular, is going to be 0. Here, the work is going to be negative, right? Because remember, the cosine of 180 is -1. And now here, because we have to break this force vector up, right? This Fx will not be as large as, part D, or example B here. So this will actually be positive, but because it's, a piece of the force, it's not going to be as great as situation D here. So if we're going from most negative to most positive, right? So the most negative would be B, because that's negative, right? It's the full negative. Then we'll come to A, and then we'll go C, and then D, right? Remember, C was only a piece of F, not the full F, okay? Where D, right, is the full force, okay? And this one was 180 degrees, and this was 0 work, okay, because it was perpendicular. All right, so from most negative to most positive, it'll go B, A, C, D. All right, and then we'll pick up again here in the next video talking about. Actually, you know what? Let's just take care of it. Right. So what happens is that if you have more than one force acting on the object, we can find what is called the net work. Okay, and the net work is just simply the sum of the work done by each force separately. So it's just like when we found net force. We're going to sum the forces, right? So we're going to say W1 plus W2 plus W3 plus ... right? And so these forces, right, that are doing the work can be horizontal or vertical. One thing to note is that you take care of the direction by putting in the cosine. So you can just simply add it all up, right? And so some of the individual amounts of work can be positive or negative, which means it is possible for the total work to be done 0, right? Done work may be 0, even though the individual amounts won't be 0, right? And so in that case, it'd be like if I take an object, I lift it up, but then, right, it falls down, or I bring it down, which means I do positive work going up, but then I do the same amount of work in the negative direction coming down, okay? So here's an example. It says, as you and your friend prepare to play Rock Hero, you push on the drum set to slide it into position. You exert a horizontal force of 24 newtons. The kinetic friction opposes the motion with a force of 22 newtons, and you slide the drum the distance of 1.5 meters. The weight of the drum set is mg, which is 54 newtons. And what is the total work done on the drums? So the easy way to do this is to actually draw a free body diagram, okay, so that you can see what forces are acting and which ones actually don't matter, okay, because they could be perpendicular or there's no work done in that direction, right? And so if we're sliding this to the right, and you can tell that because I put friction to the left, right? So the forces that are really doing the work are simply F and friction, okay? Because they are in the direction of motion. And so what we need to do is, so we know that this is going to be 24 newtons, and this is going to be 22 newtons, okay? Fn equals Fg, which would be 54 newtons, okay? But remember, this will be no work because these two are perpendicular to the motion. So our net work is essentially the work done by the applied force plus the work done by friction. Right, and I'll do full. So the work done by the weight, right, plus the work done by an F, not an N or W. So the work done by the normal force, okay? And so we're just going to do FD for everything. So FD plus lowercase fd, and we know that these two are 0 because those are perpendicular. So you can do it just a little bit of algebra and say, okay, it's distance times applied force plus frictional force, and so that's going to be 1.5 meters. Okay, oh, I'm sorry, friction's actually going to end up being negative, right? Because the angle between friction and the motion is negative, so I apologize for this. These plus signs should be negative. Okay, so it's going to be 24 minus 22, which will be 3 joules of work done on this. Okay, and one thing to note, this right here is F net, right? The net force acting on that object. Okay.